Okay, we're going to lecture a little bit here on what I talked with the other part of the class. So we're going to talk about some properties of alkanes. We're also going to talk about some alkenes, alkynes, make sure everybody's on the same page. So remember, our alkanes are single bonded guys, which have the carbon-carbon single bonds, and they basically are mainly carbons and carbons and hydrogens attached here. And they are very much nonpolar for the most part. So when we do have our hydrocarbons, they are going to be nonpolar, as the carbon-carbon bond and the carbon-hydrogen bond, based on difference in electronegativity, are going to be nonpolar. And when we talk about how they're able to interact with other molecules and themselves, they will use a certain type of intermolecular force. And an intermolecular force is the force at which one molecule basically interacts with another. And it's really a basic interaction of positive and negative things are attracted to each other. So the positive side of one is attracted to the negative side of another. And because they are nonpolar, they pretty much will be using what is referred to as dispersion forces. And dispersion forces are pretty much the main force that is used by nonpolar molecules with other nonpolar molecules, or even with themselves. And basically, a nonpolar molecule, as you should hopefully remember, means that they have an equal separation of the electrons over the entire molecule. There is no really positive side to that molecule. There's no negative side to that molecule. It's kind of like a neutral molecule. So dispersion forces are really weak type of intermolecular forces. And they're weak because they rely upon something happening to allow that molecule to have a positive side and a negative side. So they rely on like electrons moving from one side to the next to temporarily create a positive side and a negative side. So when we have a nonpolar molecule, or two of them, what could happen is the electrons in one will decide to go one way, and it will temporarily create a separation of charge in that molecule, which then will cause the electrons in the other molecule to kind of go one way or the other. Actually, it would go that way in this case. And that will cause a temporary charge in the other molecule. And now these two guys that normally don't have charges will temporarily gain these charges, and they have a way to interact with one another. They are really weak because it relies upon those electrons to kind of move out of place, basically, or somebody to come in that's polar to kind of make the electrons move temporarily. And they will basically go back to their original sort of orientation. And when that happens, then those molecules really have no way to kind of keep together. They'll kind of separate out from one another. So most organic things, a lot of alkanes, because they're strictly carbons and hydrogens, they're going to be using this dispersion forces, which is relatively weak. And that's why a lot of the sort of early organic molecules, alkanes, things like methane, propane, butane, they're pretty much gases. And that's because they have really weak interaction with one another. They're able to basically go into the gas phase really, really easily. They're sometimes said to be very volatile organic molecules or compounds. That means that they can enter that gas phase really easily. And that's why usually when you use organic chemicals, a lot of times you use it in a fume hood, because they could become very flammable as well as they go into the gas phase. And you usually don't want any type of like flame near them, or you don't usually want to smell them as well. So alkanes with 1 to 4 carbons are typically used for fuels. And as you see, methane, ethane, propane, butane. 5 to 8 carbons are highly volatile liquids. And that means although they do kind of come as liquids, they very easily could kind of transition into the gas phase. And things like octane has 8 carbons. 9 to 17 have higher boiling points. So one thing about dispersion forces is they are a relatively weak force. in comparison, for example, to something like water, which is polar. Water, which is a polar molecule, is more negative on the oxygen, more positive on the hydrogen. So when two water molecules basically get together, they're able to interact really well through the negative side of one to the positive side of another. And this is what is actually known as hydrogen bonding when we talk about water. And that's actually pretty much the strongest intermolecular forces you could have. So something like water can hydrogen bond, but something weak like our organic guys here will use dispersion forces. But the strength of the dispersion force actually does increase with molar mass. And that's because as the molar mass increases, there's frankly more electrons, and there's more places where that sort of dispersion of those electrons could happen, and more places where they can interact with each other. So if you're ever sort of comparing a nonpolar molecule to another nonpolar molecule, or really an organic guy to another organic guy, if they're both using dispersion forces, the one that is the smaller of the two in terms of atoms and molar mass will be the smaller boiling point and melting point. The one that has the larger molar mass will end up having actually the larger boiling point and melting point. The intermolecular forces play a really big role in things like that: boiling points, melting points, freezing points as well for organic compounds. So things that are like alkanes have pretty much your lowest boiling points and melting points because they have that really weak sort of intermolecular force. Something like an alcohol, which kind of has like that OH group, can do some hydrogen bonding through that OH group. So something like an alcohol actually has a pretty high boiling point in comparison to something that's an alkane, which you only use dispersion forces. So as we sort of substitute out those hydrogens on the alkanes for other compounds or other elements, really, it does sort of change properties like boiling points, melting points, because of the different types of intermolecular forces that can be used. 9 to 17 are things like oils, motor oil. That's how we get really all types of petroleum products. They're really, really long chains of carbons and hydrogens together. They do a process which is sometimes referred to as thermal cracking, which is pretty much what it sounds like. They break it up into smaller chains of carbons, like octane for gas, right? And some other ones give you some other properties along the way. Wax is 18 or more carbons, which we'll see when we talk about fatty acids. They have just a long chain of carbons together, which gives them some different properties, as we talked a little bit about today, depending if there's double bonds in that long carbon chain or not, as to maybe it'll be more solid or more of a liquid. When we talk about the solubility and density of alkanes, they are nonpolar, which means, again, they will be insoluble in water. And remember that for something to be soluble in each other, there's this idea of what is referred to as like dissolves like. And that basically means that things that will mix really well with one another are things that use the same type of intermolecular force that they use with themselves. So if somebody's using the same type of intermolecular force as another molecule, they're going to have no problem interacting with each other. But if you get two things that use very different intermolecular forces together, they really have no way to maintain that interaction. And that is definitely what happens when water and some type of organic guy comes together. The problem is our organic guy is pretty much going to be nonpolar in a lot of cases, especially something like an alkane. And this guy is obviously a polar molecule. So water, again, is going to try to use hydrogen bonding. Our organic guy is going to try to use dispersion forces. And over the long period of time, they have no way to maintain that interaction. Over like a short period of time, could they interact? Yeah, because everybody could use dispersion forces. That's kind of like the oil and vinegar salad dressing, right? You can mix it up, right? And for a short period of time, oil and water, basically vinegar kind of thing, polar and non-polar will stay together. But as you leave it, eventually will kind of separate out from one another, and they have no way to maintain that. And that's because something like water is polar, which means it has a dipole moment. It means no matter what you do to water, there's always a positive side and negative side. It's like good to go. It's always ready to interact. When you have something that's organic, it needs something to happen to make it have a positive and negative side. So it's very temporary and can't maintain those interactions. That's why when we have oil spills, right, the oil usually will end up up on top, right? The organic layer is usually the top layer in like a test tube, and the aqueous or water layer is usually the bottom when they separate out from one another. And that's because organic guys are typically less dense than water, so they typically will float to the top. So when you see different layers, usually the top layer should be your organic layer, bottom layer would be your water layer. They typically are flammable in air, and obviously they're found in crude oil. Basically, oil, as I mentioned before, I think we've talked about, is basically just a super long chain of carbons and hydrogens basically attached to one another. Now, alkanes do undergo a couple of different types of reactions, and one reaction is one that we've talked about previously when we talked about types of reactions, and they undergo a combustion reaction. So pretty much if you take any type of organic guy, which pretty much should have like carbons, hydrogens, maybe oxygen involved, and you react it with O2, you typically will get CO2 and water. So if you see an equation that's got those three things in it, that is a combustion reaction. That is basically what happens when you light your Bunsen burner. You open it up, methane comes out, oxygen in the air, a little bit of a spark. A lot of them are flammable, right? That's why we cook with propane, butane, right? Those things make flames basically when you put a spark next to them. They're very, very flammable, gives off a lot of energy usually as a result of it. Now, alkanes also undergo a different type of reaction in addition to a combustion reaction. And here's a combustion of butane, so I'll do it here. Alkanes also go under what are referred to as substitution reactions. And substitution reactions are different than what we were just talking about, addition reactions. So in addition reactions, two things get added in, basically. In a substitution reaction, one thing comes off and one thing goes on in its place. So somebody goes off and somebody comes on, and they substitute from each other. So in a alkane, we have, say, something like this. Every single one of these hydrogens are pretty much what are sometimes referred to as being equivalent with each other. So they're all basically the same thing. And if you add something, say like Cl2, we will get what is referred to as a substitution reaction. And pretty much what happens in a substitution reaction is what I said. Basically, one of the hydrogens will come off and one of those guys will come on. So unlike what we just did, where we'll put both of these guys onto this sort of structure, we're actually going to just put one of them on. So you could choose any of these hydrogens, and this guy is going to pretty much go off, and then one of these chlorines will go on in its place. And really, everything else stays exactly the same. So you, again, much like what we did earlier, you pretty much could draw exactly the same molecule, just take off hydrogen, and then where you took off the hydrogen, just put one of those guys on. So if we did that, we would end up with here our H, our C, our H, our H, our C, our H, our H. And now obviously at the end there where I took off the hydrogen, that is where I want to put on, in this case, my chlorine. I'll pop it here as ooh. By the way, there is still a couple of things still floating around at this point, right? When the hydrogen comes off, it actually comes off as H plus. And when this Cl breaks apart, this guy becomes Cl minus. So H plus and Cl minus will come together and make HCl. Yeah, so that's basically where the other part comes together to make it. So this is a substitution reaction, and pretty much alkanes will do that. You take off a hydrogen and you put one, whatever you're going to put on there in its place. We typically will do this, what is sometimes referred to as doing the mono-substituted, which basically means we're just going to take one hydrogen off and replace it with one of the halogens. Under certain conditions, you could probably force all of those hydrogens off and replace them all with the chlorine or the bromine or whatever it may be. Any questions on that one there? All right, so why don't you try some here? Let's try, let's do this guy here. Okay, let's take a look. So once again, you could choose really any of the hydrogens here, do the mono substitution. I'm just going to take off this guy at the end. What that means, I could just copy exactly what I have there without changing anything really. So that's the right number of carbons. And now at the end, we're just gonna slap our Br on there. And we will also have obviously our HBr that will come together from the hydrogen that comes off and the bromine that's left over. Any questions on that there? For our bottom one, although it's not drawn, there is hydrogens at each of these carbons, and there's actually 2 hydrogens at each of these carbons. That means really you could choose any of the carbons there. I'm going to redraw it exactly the way it is, and I'm going to take off a hydrogen and put on a chlorine in this case, and we'll do a little HCl action there. Any questions on substitution reaction? So a little bit different than addition. Somebody's got to come off to make room basically for somebody else. So one guy comes in, replaces the other guy. Any question on alkanes and those reactions there? Technically, under the right conditions, you could actually replace all the hydrogens. But usually when we draw something like this, we usually just draw. You're sometimes asked to draw the mono substituted one, which just means replace one of them. So that's usually sufficient for our cases here. But technically, under the right conditions, you could probably force, like I said, all those hydrogens basically to be popped off and replaced with the halogens. So, other questions? Yeah. Yeah, so as I was just mentioning, usually what we will draw on this is the mono substitute, so just one stuff. But under the right conditions, you need some other conditions to get them all to really pop off. But usually for sort of our textbook level here, we'll just usually draw just the one hydrogen coming off. But in reality, under, like I said, you could pretty much get them all to replace. Okay. Let's then talk officially about alkenes and alkynes. Alkenes, again, are our functional group of carbon-carbon double bond is our functional group. Our alkynes is our carbon-carbon triple bond. And as we've been talking about, every time we really do add an extra bond, we really have to make room for it. So we do sacrifice some hydrogens. So in terms of general formulas for these guys, if we go back to our alkane as a reminder, that's our carbon-carbon single bond. It has this CnH2n plus 2. And again, that will tell us how many hydrogens it should have. When we get to our alkenes, because we basically put on a bond, we will lose 2 hydrogens. So these guys have a formula of CnH2 times N. And here for our alkynes, because we put on one more bond in addition to the double bond, it will lose 2 more hydrogens, which means it's CnH2n minus 2. So in comparison here, we'll look at our ethane. Ethane here has 2 carbons, and 2 times 2 is 4 plus 2 is 6 hydrogens in this case. If we do really our double bond version of it, we will end up with something that looks like this, which is ethene, E-N-E. It has 2 carbons, 2 times 2 is 4 hydrogens in that case. And then obviously our triple bond version of it, which is actually right here. And in this case, it also has 2 carbons. So 2 times 2 is 4 minus 2 is going to give us just 2 hydrogens. So this is ethine, Y-N-E. So you can see pretty much everything still goes back to our alkane, A-N-E for our alkane, E-N-E for our alkene, and Y-N-E for our triple bonded alkyne here. Any questions on that there? So alkenes and alkynes are hydrocarbons because they do contain the double bond or triple bond. And as we were just talking about, obviously you need to sacrifice those hydrogens. They are what are referred to as unsaturated hydrocarbons. They are unsaturated again because they do not have the maximum number of hydrogens that should happen. They react with hydrogen gas to increase the number of hydrogen atoms and become alkanes. That is what we were just talking about today with the hydrogenation reaction. So one way that we saw earlier today, if we take an alkane and we add hydrogen to it, which is the hydrogenation reaction, that is going to make that into a single bond and basically add in our hydrogens there and there. And again, we go from an alkene to an alkane. So by adding hydrogen in, you will make a alkane from an alkene. And as you can probably imagine, if you removed hydrogen, which would be the opposite of that reaction, you would go from an alkane to an alkene, right? So that is when we remove an hydrogen from an alkane. So alkanes have that double bond, and the effect of the double bond is it will also change the geometry that we see. So if you remember, for alkanes, because they have that tetrahedral geometry, we get that zigzag shape that happens with alkanes and their tetrahedral geometry. With alkenes, because of the double bond, we end up with 1 electron pair, 2 electron pairs, and the double bond counts as only 1 electron pair. So that is 3 electron pairs. It also has 1, 2, 3 bonds. So the geometry that we see in our double bonded guys here is trigonal planar or triangular. That makes that equilateral triangle that we've talked about with geometry. Actually, on both sides, it makes that equilateral triangle that's happening basically on both sides of this one. That means it has a bond angle of 120, so a slightly different bond angle than what we see in the alkanes, which is 109.5, and that more zigzag shape. Alkynes also a little bit different as well because of the triple bond. It does change the geometry. So when we look at our alkyne, that is 1 electron pair. And again, the triple bond here counts as only 1. So that is 2 electron pairs. And it also has 1 bond and 2 bonds. And that gives us a linear geometry. So the geometry here changes when we put a triple bond in there. Actually goes kind of straight, if you will. And that's why sometimes you'll see in line structure, people will kind of draw the triple bond more of a straight sort of line there rather than the zigzag line. For us, it's okay if you still kind of do the zigzag. If you're doing line structure or something like that, you know, it's okay to still kind of do that. If you needed to add a double bond, you could just draw a line. It's okay. If you needed to do a triple bond, you could just add 2 lines to it and have a triple bond. Again, sometimes you'll see that kind of straighten out in textbooks because technically the geometry there is linear. So they'll sometimes kind of straighten out the triple bond part of it. Any questions? But for us, you don't necessarily have to worry about drawing the geometry of it. If you do line structure, you can still use the basis of kind of the zigzag sort of shape. Any questions on that there? All right. So identify the following compounds as an alkene or an alkyne. The first one should be an alkene, as we obviously have our double bond happening there. And the next one there would be a alkyne. Now, when we go to name these guys, we really do sort of follow very similar rules that we did with alkanes. We are still going to be looking for the longest carbon chain. But it's important when you're doing an alkene or an alkyne that the longest carbon chain has the double bond or triple bond in it. So you can't miss the double bond or triple bond. It's got to be part of the longest carbon chain. So it has to have the double bond or triple bond in it. The other thing that's really different when we name alkenes or alkynes is the priority that we give in terms of the numbering. So when we're doing an alkane, it is the groups that get the priority. We want to number whichever way gives the groups the smallest numbers. When we're doing an alkene or an alkyne, we want to number whichever way gives the double bond or the triple bond the priority and the smaller number. So when we go to number the chain, the double bond or the triple bond should have the smaller number. So let's talk about that here, looking at this one. So here we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. I think if I counted that up right. So 8 carbons is based off of octane. And our 8 carbons that's based off of octane will now become octene, E-N-E, because it has a double bond. And whenever there is sort of more than one option where the double bond could be located or the triple bond could be located, you do need to give the number as to where the double bond or triple bond is located. And we do want to go the smallest number. So in this case, if we go left to right, that is 1, 2, and 3. Obviously, if we go the other way, we're going to have a much larger number. By the time we get to the double bond, we'll have something obviously like 1, 2, 3, 4, 5 if we went the other way. So this would be what is known as 3-octene, 3 for the location of the double bond, octene for the 8 carbons, E-N-E for the double bond that's there. There is no other group attached in that particular case, right? Just all those carbons and hydrogens. Any questions on that there? All right, same thing for our alkynes. So take a moment there, give that a name. Okay, let's take a look. So might as well start straight here. That is 1. By the way, 2 is right about there on the other side of the triple bond there. That's going to be 3. That's going to be 4. That would be 5. That would be 6. That would be 7. And that would be 8, which looks pretty good. We do maybe want to check our other options to see. So I'll go, that's 1, that's 2, that's 3, that's 4. When we go down, that's 5, that's 6, that's 7. So that is obviously less. If I went 1, 2, 3, 4, 5, 6, 7, and 8. That would also be 8. Would that be a good way to do it? Yeah, we would not do it that way because we totally missed the functional group there, right? We did not include the triple bond in this case. So you got to always make sure that the functional group is part of the longest carbon chain. So although it is also 8, we would not want to go in that direction because of that. So it looks like our original counting there is probably our winner there. These there. So that is 8 carbons, which is still going to be based off of octane, but we do have a triple bond, so we're going to do a little octyne, right? We could probably clearly see that we should number left to right here because that's going to give our triple bond the smallest number of 1. Bless you. So this would be 1 octyne. We also do have a group attached here, right? And that's the thing kind of hanging down there on the bottom. And that guy on the bottom has 1 carbon, 2 carbons, and 3 carbons, which is a propyl group, right? And that is at carbon number 4. Yeah. Somebody should really just install it. I know. All right, let's just do that. All right. All right. So again, on the bottom there, we have 1, 2, 3, which is a propyl group. And that is again at carbon number 4. So that is for propyl 1 octyne. Why do I not count this carbon here as part of that group? Yeah, it's already counted as part of the main chain, so you don't want to double count that guy. Yeah, so that's why we started counting our group at this carbon here. Question on that there. Yeah. So as we just sort of talked about, we're going to replace with ENE or YNE, and they can have cycloalkenes as well, as we'll talk about in just a second, that do have obviously a double bond in it. So why don't you try these guys? Why don't we also try let's do that one. Let's do 2-ethyl, 3-methyl. Butene. Go underneath it. I think I can run out of this screen there. So we'll go with actually we'll do butine. YNA. Actually, now let's do we'll do 1 butine. There we go. So why don't you draw that, and why don't you draw cyclopropene. And I'm just going to make a quick adjustment here because I'm just visualizing not good on that. So let me do 3-ethyl, and we'll do 3-methyl. Hopefully that'll be better. I hope. Okay, let's take a look, see how we're doing. So on the first one here, we'll go with 1, 2, 3, 4, and 5. I think you could also get 5 if obviously if you went down instead of to the right there at the end. But we'll just go with the straight one there. So that 5 is based off of looks like pentane, which then would be pentene. We want a number to give the double bond the smaller numbers. So in this case, going left to right will do that. That would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Again, if you went in the other direction, you will end up with carbon 3 for the double bond, which is a higher number. So we do want to go in this direction. That means our double bond's at carbon number 2, which is 2-pentene. And lastly, here we have just a line hanging off the end there, a carbon number 4, and a line inline structure with nothing written there, right, is a carbon, and 3 hydrogens are a methyl group, right, is what at the end of that. And that would then give us 4-methyl 2-pentene. Any question on that name there? All right, looking at the next one, we got a triple bond happening there. So why not just go straight across, since I think that's everything. 1, 2, 3. Again, there's 4 there. There is 5 there, and there is 6 there. So a 6. That is going to be hexyne, YNE. You could probably see it, but going right to left here should give us a smaller number at carbon number 2. So a little 2-hexyne in that case. Obviously, there's nothing else attached. It's not part of the main chain there, right? Any questions on that one? This one I drew, which is based off of cyclohexane, but it does have the double bond, which then would make it cyclohexene, right? In this case, once again, you do not need to give any numbers because wherever that's located, it's assumed to be carbon number 1. So you don't have to actually give a number on that particular one. Any questions on any of those 3 names? So we're going to draw. So once again, we're going to draw going backwards. So butane is 4 carbons. And since you're drawing it, you could make carbon number 1 to the left or carbon number 1 to the right. I'm going to go with carbon number 1 on the left, which means my 1 is where I will find my triple bond that I know I have there. So that should be triple bonded up right there. That takes care of that part of the name. Now, since obviously I called this guy here on the left number 1, number 3 would go here. I would have an ethyl group, which is really a 2-carbon group. And also at number 3, I would have a methyl group, which is also a 1-carbon group. I guess that worked out much better than my original one, I think. And really, even with the groups, all I have to do is add hydrogen, right, to get carbon to 4. So to get this guy to 4 here, that's going to be 3 hydrogens. The guy to the middle or to the left there has 4 lines, so it should have no hydrogens. The methyl group should have obviously 3 hydrogens. The ethyl group should have 3 hydrogens there and 2 there. The carbon right about there actually has 4 lines, which means it should not have any hydrogens. And the guy at the end should have 1 hydrogen. Any questions on that? That obviously would be our condensed formula for that. If you wanted to draw a line structure for that, 1, 2, 3, 4, if you like, you could, like I said, you don't have to necessarily do the geometry, so you could triple bond up that guy. And then we're at number 3 is where I did all that stuff. So we could draw a line for the methyl group and something coming down there for the ethyl group. Would look something maybe like that as well. If you went up or down, it doesn't. Yeah. So you go either way. Other questions? Cyclopropene. Propene means we got 3. Cyclo means it's a ring. So that's like a triangle. And ENE means we have a double bond somewhere. So just might as well put it anywhere. Doesn't matter really where you put it, because if you just turn it around, it's in the other location. So it's all good. Question on how to name or draw alkenes or alkynes. The difference is, and as we'll see from this point forward, it is always the functional group that takes the priority in terms of numbering, and you always want to give the functional group the smallest number. The last thing we're going to talk about here is what to do with cycloalkenes and when we do have things that are attached. So when we do have things attached to our cycloalkene, we do have to give a number because there is a double bond. The double bond will always take the priority. So the double bond should always be carbon number 1, but there is a specific rule that you need to follow when you're numbering in a cycloalkene. And that is this. I'll just kind of draw this guy bigger up here so we can kind of see it. All right. So here's the deal when we're numbering. Clearly, the double bond will be carbon number 1. So you have really 2 options for that. Carbon 1 there, or carbon 1 on that side of the double bond. We do want to give our group the smallest number. So you may be tempted to go, if I just go left here, starting with 1 here and make this 2, that obviously is a smaller number. The problem with that is there is a rule that says when you have a double bond in a cycloalkene like this, you have to actually number through the double bond. So you have to actually go through the double bond when you're numbering, which means this would be illegal in this case. Your option would be, if you were to number, you would actually have to take it through the double bond there. So this would be 1. This actually would then be 2. This would be 3. This would be 4. And this would be 5, which would give that group a number of 5. Your other option of numbering would be to start with this carbon here. I'll just draw it here as number 1. Go through the double bond, which means that carbon would be number 2. That carbon would be 3, 4, and 5. So going kind of counterclockwise in this case does give us a smaller number of 3. And that is why this guy right here is known as 3-methyl cyclopentene and not 2-methyl cyclopentene. So when you have an cycloalkene, the numbering has to go through the double bond, and you can go either way, and whichever way obviously gives the groups a smaller number. Any questions on that there? So if we were to look at, say, these guys here, this is the one we just did. There's nothing attached. So this would be, again, our cyclohexene. This is our double bond, and we do have 2 methyl groups attached here. So our option to number is you could go counterclockwise, 1, 2, 3, 4, and 5. The other option is to start here at carbon number 1 and go clockwise, 2, 3, 4, and 5. Obviously, going clockwise here is going to give our group the smaller number of 3. So that is cyclohexene. I think there was 5 before I wrote all over it. Each of those lines are methyl groups, right? So we have a methyl group there. We got a methyl group there. That's 2 methyl groups in the same compound. So that's a dimethyl. So we have a dimethyl here. And we do need to give the number of both of those methyl groups, even if they're on the same carbon. So this should be 3,3 dash dimethyl cyclopentene. Any questions on how to number those? All right. Question on cycloalkenes, alkenes, alkynes. All right, you guys are all caught up. Yeah, so there we go.